Let's take a look at an example then of the loop current method. In the loop current method, you can see we've got two loops that have been identified here. We've identified the direction of the current by way of the polarity on the battery. So using the loop current method, we're going to find the branch currents for the schematic. So we assign the loop currents, as I just stated. Resistance values are in ohms, voltage values are in volts. Use the rule described in the previous session to set up the two loop equation. So you can see what we've done here. We've got 470, which would be in ohms, added to 220, which would be in ohms, times the loop current for this particular loop, okay? And we set that equal to, we're going to set it equal to 10 volts. And then what we're going to do is we're going to subtract the current and voltage of the current and resistor relationship across R2. You'll notice it has a negative sign. So we're going to take 220I sub B away. So now we're going to combine our terms here. So we've got 690 times the current in loop A minus 220B and set it equal to 10. And we're done. That's all we can do with that section. So now we're going to do the same thing with the loop B. So now we have the current in the opposite direction in A for this side, the 220. So 220 minus times the current in A, and then we're going to add together 220 and 820 for the direction of the current in B and set that equal to minus 5 volts, because notice we have the polarity opposite here. So we end up with minus 220, the current A, plus 1040, current B, minus 5 for loop B. So now they want us to, in this example, not use substitution, but to use the determinant method. So the first thing we're going to do is we're going to set up our matrices based on the values for A and B. Our characteristic determinant in the denominators here in both of these, so 690 times 1040 minus 220 and minus 220. Okay, so when we expand those, we end up with these two relationships for the determinant for current A and the characteristic determinant, and we get 13.9 milliamps. We do the same thing for current B. In this case, we use the 690 and minus 220, 10, and minus 5 for our values in the determinant. Those are our voltages. So this times this minus this times this, and we end up with minus 1.87 milliamps. So the negative sign on current B means that the assigned direction is in the opposite direction of the actual current. So they just picked the wrong direction. Easy to fix. Now find the actual branch currents. Since the current through A is the only current through R1, it is also the branch current for I1. So current I1 is also the current I sub A, or 13.9 milliamps, which we solved for up here. Since the current through B is the only current through R3, it is also the branch current for I3. So I3 is equal to I sub B, which is minus 1.87 milliamps, which is the one we solved for up here. Okay. The negative sign indicates the opposite direction of that originally assigned to IB. As originally assigned, both loop currents I sub A and I sub B are through R2 in opposite directions. The current then I2 is the difference between I sub A and I sub B. So you can say I2 is equal to I sub A minus I sub B, which is 13.9 milliamps, minus a minus 187, which is the sum then, giving us 15.8 milliamps. Keep in mind that once you know the branch currents, you can find the voltages by using Ohm's law. Notice that these results are the same as in the example 9.7, where the branch current method was used. So a quick example here of using the loop current method and doing it by determinants this time instead of substitution. All right, so what if we have circuits with more than two loops, okay? In this case, we've got a bridge, we've got a loop A, a group B, and a loop C here where we've got currents flowing. So the loop current method can be systematically applied to circuits with any number of loops. The more loops there are, the more difficult, though, is the solution. But calculators have greatly simplified solving simultaneous equations. So those of you that have learned how to calculate and use a simultaneous equation by using a built-in function in your calculator, you'll find out very quickly you can do that. Again, you can set something up by writing the relationships into an Excel spreadsheet and achieve the same thing. Most circuits that you will encounter will not have more than 3 loops because it just becomes a futility in just creating work. Keep in mind that the loop currents are not the actual physical currents, but are mathematical quantities assigned for analysis purposes. A widely used circuit that you've already encountered, of course, is what we're looking at here, the Wheatstone Bridge. The Wheatstone Bridge was originally designed as a standalone measuring instrument, but has largely been replaced by other instruments. Whatever you put across the center here, then you could use as a balance, and so that becomes your load, or however you want to look at it. Although, however, Wheatstone Bridge circuits is incorporated in automated measuring equipments, as explained previously, it is widely used in the scale industry and other measurement applications. So if you go back to the previous section, the previous chapter, you'll see how the Wheatstone Bridge is used in balancing in scales. One method for solving the bridge parameters, which directly leads to finding current in each arm of the bridge and the current at the load, is to write loop equations for the bridge. Also, the Wheatstone Bridge has 3 loops. So we're going to take a look at it here as an example. So if we take a look at the example here for the Wheatstone Bridge, we're going to find the loop currents, use the loop currents to solve for the current in each resistor. And you can see over here, they're setting things up for us to use the determinant method. And remember, the determinant method is a little more involved because you've got to create those external 2 columns taken from inside of the array. So if you assign 3 clockwise loop currents A, B, and C, then write the loop equations. The equations for the loops are as such. So if we just go around the loop and pick the source, the first resistor, the second resistor, multiply it times the current I sub A, and subtract the current I sub B and I sub C. From that, we get loop A. Loop B, we do the same thing, but no source. Loop C, we do the same thing. Again, no source. So if we rearrange the equations in standard form, then we have loop A, B, and C accordingly. Of course, the first one you can see has the source included, and in the group loop B and loop C, we have the load resistor across the center included. So you can solve these equations with substitution, but this is tedious with 3 unknowns. So the determinant method or directly solving with the calculator are simpler ways. Units are not shown until the end. So again, if you've learned on your calculator how to use the matrix, the matrix functionality, I would try it with that. It'll make the math on this a lot easier. So we evaluate first the characteristic determinant. You can see we've had to extract the first 2 columns, move them to the outside, and we do our this times this times this, this times this times this, this times this times this, and we add them all together to get the value, pretty big number here, for our determinant, okay, our characteristic determinant. Then we're going to solve for A, B, and C by solving for the determinant for each one of these. So again, you start with your characteristic determinant in the denominator, and in the numerator we've got each of our individual determinants or matrix arrays for that particular circuit. So in solving them out, we end up with 35.1 milliamps for A, 62.2 milliamps for B, 15.8 milliamps for C. So the current in 1 is the difference between A and B, okay? So R1 is this 330 ohm resistor. So we take the difference in those two currents, A and B, and we get 18.9 milliamps. Do the same thing for R2, do the same thing for R3, except in this case R3 is equal to the current B. Why is that? Because I sub B is the only current going through that one. Same thing applies for IC. The current in the load resistor has two currents, I sub B and I sub C, flowing through it. So we take the difference in those. We can see they're flowing in opposite directions, so we subtract them, and we get 0.4 of a milliamp. Again, this is a long, tedious process. You can certainly multiply, divide, add, subtract by hand on these. But if you're familiar in your calculator on how to do it, I would do it that way. I would just, for grins, check out on my calculator how it's done anyhow, so that you knew the power of the simultaneous equations and matrix operations. The next one is a bridged T circuit. Okay, so we've got R1, 2, and 3, 4, and hanging out here on the bottom is our load resistor. While the circuit is primarily applied to AC filter circuits using reactive components, it's introduced here to illustrate a 3-loop circuit solution. So the resistors will often be in the k ohm or even the megohm range, so the coefficients for simultaneous equations can become quite large if they're shown explicitly in solving equations. To simplify entering and solving the equations with 1 k ohm or in the k ohm range, it's commonplace to drop the k ohm in the equations and just recognize the unit for current as milliamps if the voltage is in volts. Okay, it's just ways of making it simple. You do know all throughout your calculations that the value is going to be higher, but it's just a trick in making the math easier. Okay, so in our example here, again, we set up the loop circuits for A, B, and C. Choose your directions of the currents here. Only one of the loops is going to have the source in it, B. So the other two are not going to have a source. C is going to have, of course, the load in it. So we write our loop equations based on the resistance and the unknown currents for each of them. So A, B, and C. Then we're going to rearrange the equations into standard form so that we have all the current A, all the current B, and all the current C in the same column, as well as B for our voltages. It talks down here about a calculator solution. A calculator solution requires entry of the number of equations, in this case 3, the coefficients, and the constants. The calculator solve function produces the result as shown. Because the resistors were in the k ohm region, the unit for the loop currents is in milliamps. Solve the current for each resistor. Okay, so we end up with the current in R1 equal to A, and since that is also current 1, that gives us a 0.5 milliamp or 0.512 milliamps. The current through 2 is the difference between A and B, so we have 0.512 minus 0.877 milliamps to give us minus 0.375. Again, the current sign indicates the current is in the opposite direction to current A. The positive side of the resistor is on the right side. The current in resistor 3 is the difference in the current I sub A and I sub C. So this is the relationship. We get 0.08 of a milliamp. The current in R4, right here, just opposite the source, gives us I sub B minus I sub C, which gives us 0.455 milliamps when we take the difference in those two currents. And then the current through the load, again, is only current C, so current through the load is 0.432 milliamps. Okay, so they've jumped some steps here and they used the calculator solutions. Again, pull out your calculator and try that for yourself as a learning exercise. So when we come back, the next method that we're going to explore is something called the node voltage method. And again, it's a methodical process here, 5-step process that we'll take a look at.